Hello, my name is Leonardo Santos, and I'm here to present my risk work that I did with Professor Andrea Baici in the Intent Lab at CMU. So the work's called COURTEOUS, combining online updates of safe robot controllers with user preferences. And the motivation is that while some constraints are inherently unsafe, like collision avoidance, others are personal and semantic and can only be inferred after deployment when the robot is interacting with a specific human in a specific environment. So in this case, for example, no one wants the robots to crash into walls, but some people might also not want them to drive over their very expensive and fancy rug, other people wouldn't mind this. And the safety framework used for this is Hamilton-Jacobi reachability, which basically what it does is when you give it a set of failure states with the system dynamics, and it returns you a set of states that will from which if the robot starts there for a given time horizon, there's always a control input that it can choose despite the worst case disturbance that will keep the robot out of this failure set of states. And this is the safe policy that this solution uses. But how does this safe policy works exactly? Once you solve this value function, and it's above zero, which is inside this red boundary. The red boundary denotes the zero level. Once it's when the robot is inside the red boundary and the value function is positive, the robot is safe because there is always a control input that it can choose to remain safe. And we allow the robot to do whatever action the nominal planner that's concerned with completing the task wants the robot to do. However, when the robot is in a stage which the value function is negative or equal to zero, the robot is unsafe. So we execute an optimal control action to bring the robot, bring the robot back to the safe states. In practice, we execute this action when the robot is at the boundary of the unsafe set. What it means when the value function is exactly equal to zero, so the robot never leaves the safe set. However, a problem with this framework in our setting is that it requires us to know the failure set beforehand. However, as I said in the motivation, some of the constraints that are personal can only be inferred after deployment. So our key contribution in this work is to combine human feedback via language inputs with online updates of the unsafe set. And we do this by using a visual language model to allow the human to act as a sensor. So while some sensors might not detect rugs as obstacles, if the human can act as a sensor and tell the robot that the rug is an obstacle, and the robot can do some inference to, given the detection using the VLM, estimate the rug's position, he can add this as to his set of failure states. And because we have to update the value function online, we use warm start updates to speed up the computation. So our method has basically two components. We first offline, given the set of failure states, the inherently safe, constraint, unsafe states such as obstacles, we compute this shared value function that will be shared across every single human in a replication, such as collision avoidance. And we use this to warm start the online updates afterwards. So in this blue bounding box, blue box, uh, this is running constantly online in the robot. So whenever the human input gives a new language command, it's appended to the set of language instructions. And once the VLM detects any of these language commands in the image, it adds this constraint to the personal failure set, FI. And we use the previously computed value function to online update the personal value function, and this keeps looping during the task as execution. And we show a running example with unicycle dynamics, where we tell the robot to not drive over the rug. So on the left we just use MPPI as a nominal planner and an off-the-shelf slam system, and since the rug is not inherently unsafe, this slam doesn't detect it as an obstacle. So MPPI cannot comply the personal human constraint, and therefore it drives over the rug that's depicted, that's like marked, that's inside this orange bounding box. But using our framework, when the nominal planner takes the robot close to the rug, our safe policy takes over and steers the robot to avoid the personal constraint. And here we show the advantage of using the warm updates. So with no warm updates, it takes around 4 seconds. It's definitely not feasible for online applications. But warm starting the value function, if there's no change, uh, the solution is basically instantaneous because the value function is already converged. And when we add new constraints, we have a rough 4 times speed up in the value computation of the value function. And I want to thank everyone, all the risk organizers, all the mentors, and for making this possible. I'm very thankful for all the support in this program, and thank you for listening.